This problem is a special case of the exercise that we just did before, which is the Luxembourg monotone convergence theorem for sequences. So here, what do we have? We have Fn, a sequence Fn of functions defined on AB. What do we assume? We assume that they are all Riemann integrable. Okay, so in the Luxembourg theorem, we do not assume that the fn's are Riemann integrable. So that's why we had to approximate by continuous functions. Okay, so here we have the fn's which are Riemann integrables, and we have that number f, the fn's converge pointwise to f. Pointwise to f. We assume that f is also Riemann integrable. And 3, we assume that the fn's are either increasing or decreasing. It makes no difference. Okay? So here in the problem, they are decreasing. So fn plus 1 is less or equal than fn. Okay? So under these assumptions, to come up with the theorem before, because we wanted to go to pointwise to 0, so what we're going to do is to introduce the functions gn, which is equal to fn minus f. Okay? Then in this case, what happened? The gn's are positive. Okay? 2, the gn's are decreasing. 3, the gn's converge to 0 pointwise. So now we can use the theorem of Luxembourg that tells us that the limit when n goes to infinity of the Riemann lower integral of the gn's of x dx is equal to 0. Okay? But since fn and f are both Riemann integrable, then we know that gn is also Riemann integrable. And in that case, the lower Riemann integral of gn of x dx is exactly the integral of gn of x dx, which is equal to the integral from a to b of fn of x dx minus the integral from a to b f of x dx. Okay? So we conclude that the limit when n goes to infinity of the integral from a to b fn of x dx minus the integral from a to b f of x dx is equal to 0, or limit when n goes to infinity of fn of x dx is equal to the integral of fx. Of course, the assumption of being decreasing of the fn's is extremely important. Otherwise, the theorem is false.